At 6:04 in the evening on June 24, 2026, something snapped beneath Venezuela's Caribbean coast. Not one earthquake, two separated by exactly 39 seconds. The first, magnitude 7.2, struck without warning west of Caracas. Buildings swayed, people ran into the streets. And then, before the shaking had fully stopped, a second shock hit, magnitude 7.5, 3 times the energy of the first. In La Guaira, a 10-story apartment building folded flat in seconds. A 22-story tower in Caracas's Altamira district followed. By morning, over 50,000 people were listed as missing, not displaced, not injured, missing. The USGS issued a red pager alert, its highest casualty projection, estimating the final death toll would likely number in the thousands, with a substantial probability of exceeding 10,000. But here's the part that most coverage missed entirely. Scientists saw this coming, not the exact moment, no one can predict that, but the specific fault that broke, the stress accumulated on it, the probable magnitude. They had calculated all of it. Some had presented their findings at a European Space Agency conference just 6 days before the ground gave way. The fault they were watching is called the San Sebastián, and it is not finished. Venezuela sits at one of the most geologically complex points in the Western Hemisphere, a place where two massive tectonic plates grind against each other without rest. To the north, the Caribbean plate. To the south, the South American plate. They do not collide. They slide past each other horizontally along a boundary stretching the entire length of Venezuela's northern coast. That boundary is not a single fault. It is a 1,300-kilometer network of interlocking strike-slip structures known as the Boconó San Sebastián El Pilar fault system, running from the Venezuelan Andes in the west, across the north-central coast, all the way to Trinidad in the east. The Caribbean plate moves eastward relative to South America at roughly 10 to 20 millimeters per year. That slow grind builds stress in the rock over decades, over centuries, until the fault breaks. The San Sebastián sits mostly underwater, hidden beneath the Caribbean Sea north of Caracas. For most of the 20th century, it was treated as a minor feature. The USGS overview of Venezuelan tectonics, published in 2000, barely mentioned it. That changed when scientists reanalyzed the 1900 Caracas earthquake, magnitude 7.7, the most powerful in Venezuelan recorded history. A 2015 marine seismic study concluded that rupture had originated on the San Sebastián, not on the El Pilar fault, as previously assumed, which meant the San Sebastián had been building strain since 1900, for 126 years. 6 days before June 24th, geophysicist Michael Higgins of Florida International University presented satellite-based strain calculations at an ESA conference. The conclusion: the San Sebastián had accumulated enough stress for a magnitude 7.1 earthquake. The actual rupture was 7.5, and it did not come alone. What made June 24th different was the doublet, 2 main shocks on adjacent fault segments, less than a minute apart. The 7.2 appears to have broken the northernmost section of the Boconó Fault, a segment locked since the catastrophic 1812 Caracas earthquake, which had killed over 15,000 people. That rupture transferred stress eastward. The San Sebastián, already primed to the breaking point, absorbed that redistributed load and failed 39 seconds later, sending a rupture propagating toward Caracas at 3 to 3.5 kilometers per second. This is what makes doublet so dangerous. When one fault breaks, it does not simply release energy, it redistributes stress onto neighboring locked segments. The second earthquake did not happen despite the first. It happened because of it. La Guaira absorbed the worst of what followed. The city is built on soft coastal sediment, loose, water-saturated material along a narrow strip between the mountains and the sea. When seismic waves pass through soft sediment, they amplify. A building on soft ground can experience shaking several times more intense than an identical structure on solid bedrock nearby. It is the same mechanism that devastated Mexico City in 1985 and San Francisco in 1906. In La Guaira in 2026, it turned apartment towers into rubble in seconds. The main shock broke at a depth of just 10 kilometers, shallow enough that almost no energy dissipated before reaching the surface. Strike-slip faults release energy laterally. The horizontal forces they generate are precisely the forces that most unreinforced masonry buildings cannot resist. Venezuela updated its seismic building codes after the 1967 Caracas earthquake. But enforcement had been inconsistent for decades. Many buildings were already compromised before the first wave arrived. Stop for a second. Consider the scale of what a doublet does to a compromised building stock. The 7.2 cracks the walls, bends the frame, shifts the foundation. The building is structurally wounded. Then, 39 seconds later, the 7.5 arrives. The building is already broken. It does not survive the second blow. Within hours of the main shock, over 200 aftershocks had been recorded. The USGS aftershock forecast published the following day estimated a 99% probability of a magnitude 4 or greater within the next week, a 98% chance of a magnitude 5 or greater, and a 43% probability of a magnitude 6 or greater, striking a city where hundreds of buildings were already critically damaged. Yamilet Jimenez stood outside a collapsed 7-story building in La Guaira and told reporters her 19-year-old son was trapped beneath the slabs. There was no heavy machinery. Neighbors were digging with their hands. The physiological survival window for a person trapped under reinforced concrete without water in summer heat is roughly 72 hours. That window was closing while equipment was still being loaded onto planes in Bogota and Miami. By Friday evening, the confirmed death toll reached 920, more than 3,300 injured. A missing persons tracking website listed over 50,000 names. That is the population of a mid-sized American city, simply gone from the record. The U.S. State Department committed $150 million to relief. Urban search and rescue teams from Los Angeles and Fairfax County arrived on the ground. USS Fort Lauderdale positioned off Venezuela's coast. International aid reached the airport in La Guaira, the same airport whose runway sits atop the only onshore segment of the San Sebastián Fault, damaged and closed, slowing everything down. But the story of June 24th is not only about what has already happened, it is about what remains loaded on the fault. The June 24th rupture covered approximately 210 kilometers along the Bacano-San Sebastián system. The full fault network is 1,300 kilometers long. Over 1,000 kilometers of it did not move. To the east lies the El Pilar Fault, a structure whose earthquakes appear to migrate eastward over time toward the city of Cumana, a city of 350,000 people that seismologists have compared to Istanbul's position relative to the North Anatolian Fault, sitting at the edge of a segment that has not fully ruptured in modern memory. To the west, the Ancon segment of the Oka-Ancon Fault last ruptured approximately 4,500 years ago. Its recurrence interval is 2,000 to 4,000 years. By that calculation, it has reached or exceeded its cycle. When it fails, models project a magnitude 7.5 event. And the Bacano Fault itself, the segment scientists believe initiated Wednesday's sequence, has not fully released the stress accumulated since 1812. Structural geologist Frank Audemard of the Universidad Central de Venezuela, who had spent years warning about that slip deficit, called June 24th the 1812 earthquake's brother, a brother, not a twin. The GPS monitoring stations embedded in Venezuela's bedrock are transmitting data right now. Scientists are analyzing the deformation pattern, measuring what moved, what shifted, what is now more critically loaded than it was on the morning of June 24th. The sections adjacent to the June 24th rupture absorbed redistributed stress. They are closer to their failure threshold than they were 3 days ago. The question is not whether the remaining segments will eventually rupture. They will. The question, the one no instrument can yet answer, is when. Subscribe to stay ahead of what's coming.